share my screen. Hopefully you can see my screen. So yesterday we have finished the analysis about the criterions, the filtering criterions for the aggregates to identify whether this one is appropriate for the drainage layer. Actually, we have analyzed the filtering criterion based on the permeability and retention. Generally, there will be two major criterion. For the permeability, we need to find out the ratios between the filtering materials and the soils. For their effective size, around 15% parts, they should be higher than 5. Or for some other models, they should be at least higher than 4. And also you need to check the retention criterion. The D15 over D85 soil should be less than 5. And we have the third one, which would be the grain size curve requirement. And in this additional criteria, you want to make sure that the ratios between the filter and the soils at the effective size of 50% parts is less than 25. So once this all these 3 criteria are satisfied, we can claim that there will be an effective drainage material. And in this problem, we first use all the information provided by the problem and a figure to identify one open graded base material to determine whether it's appropriate for the drainage layer. And based on what we calculated, we found that for the retention criteria it's not satisfied. For the permeability it's satisfied, but for the third one, the additional criteria is not satisfied. So we have to make sure that all the 3 criteria are satisfied to claim that it's an appropriate material. But in this case, definitely it's not. Then for the next question, what we want to check is what kind of materials we should use if the base is to be placed between the subgrade and the open grade base. Which filtering materials in the figure on the right is an appropriate material? So we will let's see what we can do. So first of all, let's just draw a figure about the specific problem. In this problem, we assume that the material will be placed between the base layer is placed between the the base layer is placed between between the open graded material that we defined previously, and also we have the subgrade placed at the bottom. And then we want to check whether this one is in a good drainage layer. Well, in this case, what should we do to identify whether it's in a good or it's in a wrong material? Do you have any ideas about it? And or what do you think we should include? Like, do we need to analyze the interactions between the open graded material and the base? Or do we just need to focus on the base and subgrade layer? What kind of any ideas about it? Okay, probably I can initiate the discussion. So basically, in this kind of problem, we will always consider the layers on top as the filtering layer, and the one at the bottom behind it as the soil. So what we can claim is that if we only consider the open graded and the base layer, the open graded will be the filter, and the base will be the soil. If we consider the two layers below, then the base will become the filter, and the subgrade will be the soil. So we have to make sure that these two combinations are both satisfied. So we have the information we have already calculated the information for the open graded materials, and we have also know the information about the subgrade. Then we need to use both of their informations to do the calculation. We want to identify this one. We want to find out the possible range of D15, D50, and D85 for the base layer materials. And then let's see what we can do. First, for the subgrade layer, we know that for D15 is a 0.0013, and for the D50 that is a 0.0055, and for D85 that is a 0.021. This is the information from the problem. And then let's go to check the retention criterion. The first one is the retention criterion. So for the retention criterion, we have the D15 filter divided by the D85 soil should be smaller than 5. And in this case, which one is the filter? So in this case, which one is the filter? Any ideas about what information we really calculate for this equation? So for this one, for this case, for the base versus the subgrade, definitely the filter will be the base layer. So what do we calculate? Like we have the D15, that will be the base layer, divided by D85, that will be the soil, should be smaller than 5. And then we can find out the one range for the effective size for the 15% passing. So D15B, the base layer, will be less than 5 times D85 soil. So that is 0.105. So that's the first condition from the retention. And the second one, let's go to check the permeability. So for permeability, we have D15 filter divided by D15 soil higher than 5. And of course, we have D15 base divided by D15 soil larger than 5. This will give you the value as D15 base is actually higher than 0.0065 based on the value of D15 soil. And we also have another condition, which will be the third one. We have the third condition, the D50 filter divided by D50 soil should be smaller than 25. and that one give you D50 base divided by D50 soil smaller than 25, and you have the value, the range as D50 base smaller than 0.138. So those would be the three conditions we obtained for the base layer versus the subgrade layer. And we also need to think about the another case. So for the interaction between the open graded material versus the base, it should also satisfy all these three conditions. For the and from the first part of this problem, we actually find out the value of D15 open graded. So we say that it's in this case that will be the filter, and we also get the value of D50 filter. And with that, we can use this three criterion to find out the information, the conditions for additional conditions for the base, the 50 base and the 85 base. So this would be the information we want to calculate. And this is an additional one by assuming that the open graded material is the filter and the base would be the soil. So here you have to remember that we always have to we always set the one on the top as the filter layer and the one at the bottom as the soil layer. So for the first one, retention criterion, we will have D15 filter divided by D15 base, D85 base. This is actually the soil. So it's less than 5, and this will give you the result as D85 base larger than 0.052. And similarly, you can get the second criterion, permeability. That will be D15 filter divided by D15 soil. In this case, that will be the base layer larger than 5, and you get the value as D15 base layer. It's smaller than 0.05, 0.052. And we also have additional information. The third one, that will be D50 filter divided by D50 soil, which is the base, smaller than 25, and you get the result, D50 base. It's larger than 0.0212. And this would be the additional criterion based on the open graded filter and the base layer as the soil. And we have to combine this one with the previous results with these three criterions. And based on that, we can eventually find out the criterion as for D15 base, it should be larger than 0.0065 and smaller than 0.052. And for D50 base, it should be smaller than 0.138 and larger than 0.0212. And for D85 base, it should be larger than 0.052. All these three conditions should be satisfied. And then there's a question for you. Do you think, based on these three conditions, which material do you think is appropriate from the for the base layer, based on the grain size distribution set in this figure? We actually have the probability equal to 2 feet per day, 10 feet per day, 20, 50, 100, 6,000, and so on. And which one is appropriate? And how can we choose the appropriate material as the base layer? Any ideas to find out this information? Maybe this figure is too small and not easy for you to observe. So I will start with just one condition. So let's first go to check the 15% passing, the effective grain size as 15% passing. So you can roughly find out the line with 15% passing. So for the 15% passing, the grain size, the effective size should be between 0.065 to 0.0065 to 0.052, and this will give you the range around. So if we go to check the 0.065, it will be something between here and 0.055. There will be some value around here. So any materials which can in this region, which can pass in this region, will satisfy the first condition. So that's the first one for the 15% passing. And then next, we also need to check the 50% passing. The 50%, it will be easier for you to check from the map. And for the 50% passing, the low bound is a 0.0212. So we need to find out the appropriate range. That will be someplace around here, 0.0212. And for the other one, the upper bound would be 0.138. So go to check 0.138. That will be someplace in between this region. So we have another region to cover for the condition of 50% passing. And the last one would be 85% passing. So go to 85%. And it should be higher than 0.052. So the 0.052 would be some value, would be the value here. And of course, it should just need to be larger than this value. So any region higher than that should be fine. And in that sense, you can find out that there will be 3 lines passing through these 3 regions. This region 1, region 2, and region 3. So based on that, we can find that if the permeability equal to 10, 20, or I guess this is a 50. If it's this 3 type of the aggregates, then it can satisfy all the 3 conditions. So we say that K equal to 10 or 20 or 50 for these 3 aggregates. That will be okay. So this will be an appropriate material for the drainage layer. So with that, we finished the introduction about the selections of the appropriate aggregates for the drainage layer. Do you have any questions so far? Okay, if no, then I will stop this slide and go to the next one about the selections of the other drainage materials. So the second one we want to in this slides, we also we want to continue the discussion about the drainage design, and we said that there will be three types of the drainage materials. One is the aggregate, which we have just introduced. The second one would be the geotextile or the fabric materials, and the third one would be the pipes, including the perforated, slotted, or the open joint pipes. And we want to identify what's the criteria we have to use to select the most appropriate geotextile materials or the pipes for the drainage layer. So let's first go to check the geotextile. Usually we will consider the filter fabrics and they will be actually applied to protect the drainage layers from the clogging. And the purpose of the design is at first they're going to try to retain the soil, prevent the washing out of the fine particles. It's also able to help to remove the water, and also it's able to prevent the clogging for the drainage layers. And for the geotextiles, the filtering criterion is different. It's actually, the material is very different from the aggregates. In order to identify the appropriate geotextiles, we're going to use the apparent opening size, AOS. And this would be the size of the glass piece when 5% passing through the geotextile. And with this, by choosing the appropriate value of AOS, we are able to maximize the retention of the soil. So which is controlled by the smallest open size. That will be the largest AOS for the geotextile, and also is able to maximize the clogging of the fabrics. And with that, we have to use the maximum opening size, which means that we have to consider the lowest AOS for the geotextile. And with these two conditions, we will find out the lower bound and the upper bound of the AOS for the geotextile. And generally, we have some values already calibrated for the well or most popular geotextile materials. For the retention criteria, we will check the fine grain soil with more than 50% passing number 200 sieve. And usually if the geotextile is made of the woolen materials, we want the AOS to be less than D85. And for non-woolen material, AOS should be less than 1.8 times D85. And also the AOS should be higher than number 50 sieve, which means that the size should be smaller than the number 50 sieve will have the size of 0.297 millimeters. And that's for the fine grained soil when they have 50% passing number 200 sieve. But for the granular materials with less than 50% passing number 200 sieve, then the retention criteria is a little bit different. For the retention criteria, we want the AOS to be less than B times D85, and B is one coefficient, and the value of B is determined based on the coefficient of the uniformity. So here, the Cu is the coefficient of uniformity. It's defined as D60 divided by D10. So if Cu is between 2, is smaller than 2 or larger than 8, then B is 1. And if Cu is between 2 and 4, then Bu will be 0.5 times Cu. And if the Cu is between 4 and 8, then Bu will be 8 divided by Cu. Again, Cu here is the coefficient of the uniformity. And we can use this equation to find out the upper bound of AOS for the granular materials. And if the soil contains particles from 1 inch to those passing number 200 sieve, then we will only use the portion passing through number 2 sieve. For the particles with the grain size larger than number 2 sieve or stay in the number 2 sieve, then we have to remove them. We will need to correct the grain size distribution in order to apply this retention criteria. And there will be one example to show you how to do this correction later. And for the filter criterion, it will be simpler. We will have the permeability criterion, where we want to make sure that the effective size is larger than the fabric is larger than the soil. And here you have to remember that K is defined as the effective size and not the permeability. So just the two different definitions. And for the clogging criterion, if we have the woven materials, the percentage of the open area should be larger than 4%. And for non-woven material, the porosity should be higher than 30%. And you can check the definition of the porosity in the previous slides. So those would be the criterion for you to use to identify whether one geotextile is appropriate as an filtering material, and also definitely this one is related to the property of the soil. So in the let's go to see one example. So the figure here shows the grain size distribution of two different soils. One is called the fine grained soil. The other one is the granular soil. We want to determine the required AOS of the woven fabric to retain the soil. So with that, we can then record the criterions we defined in the previous pages. So for the first is the woven material. And with the woven material, if we go back to check the retention criteria, the AOS should be less than 85% of the effective size. So with that, we have AOS less than D85. And then let's go to check the fine particles. For the fine particles, or for the fine material, which would be the one we're going to use this line. And we want the AOS to be less than D85. In this page, you can find out the percent, the 85% passing as it's just some approximate value from this graph. So with that, you can get the this value as 0.24, approximately 0.24. So we have AOS less than 0.24. So that's the fine particles. And then let's go to see the second one for the granular materials. Here I will just ask you one question. So we can go to check the 85% passing for the granular material, and that will be something around in this case that will be almost like 12 millimeters. So do you think the 12 millimeters is the value we have to use for the granule materials. It's the right value for us to use. Any ideas about it? Okay. So in this case, actually the answer is no. So there will be some conditions that we have to consider to apply the retention criterion. In the retention criterion, there's one condition. We say that if the soil contains any particles, if the soil contains the particles from 1 inch to those passing number 200 sieve, then we will only consider the portion passing through number 2 sieve. For any portion larger than number 2 sieve, you have to remove them. And with that, let's go to see the grain size distribution of the granule materials. You can see that there will be almost 57% of the potential particles can passing through number 4 sieve, and which means that the number 4 sieve will retain 43% particles. So we should remove this 43% from the original aggregates and adjust it to just consider the portion from number 2 sieve to the finest particles. And to do this correction, we can call the equation here the fx prime. This would be the corrected grain size distribution. This is a corrected, and this one should be equal to the original grain size distribution divided by the integration of x0 to xl times fz dz. And here xl is the number 2 sieve. So this is xl. And the x0 would be the smallest value. So this would be the x0. So by doing this one, you can actually lift the portion, ignore the part with which is higher than number 4 sieve, and lift the rest portion to make them be in a complete grain size distribution. And with that, we can then use the updated grain size distribution, the corrected grain size distribution, to calculate the requirement for the AOS. So we know that for the wood materials, for the granule materials, for the granule soil, we have AOS smaller than B times D85. And here, if we go to check a D85 in the corrected material, and that will be some value around 2.4. So this is almost 2.4 millimeters. So we have D85 equal to 2.4 millimeters. This is just some approximation from the figure. And the other thing we have to consider is the coefficient B. B is actually determined by the coefficient of the uniformity, and uniformity is actually the ratio of D60 divided by D10. And for this soil, let's go to see what's the value of D60. D60 is this line, and then you can find out the value of D60 as 0.78. And you can also go to check D8, D10. And this one is about 0.042. So we have the CU as 0.78 divided by 0.042, which is 18.6. And Cu here, clearly Cu is higher than 8. And this indicates that B is 1 from our previous definition. So with that, we can get the criterion for AOS as B times D85, that will be 1 times 2.4, which is 2.4 millimeters. So that's the way for us to identify the AOS for the geotextile with the granular materials. So this is the geotextile. Do you have any questions so far for the calculation of the AOS and the criterion applied? No. Then let's go to check the next one. This would be the general applications about the geotextile. Usually the geotextile could be considered as, could be applied at several different situations. First, it could be applied as the edge drain. With that, it could be cover all the filter materials. So this would be the solid line here is the it's the geotextile. This is an it's called the black fill. It will cover all the materials, and the filter materials is included inside, and you have the pipes placed at the bottom. So this is one common design of the which we call it the edge drain with the geotextile. The other one is called the sub-base drain. This would be a little bit different. In this kind of design, we will actually make the filter materials connect to the make it open for the subbase. With that, the water from the subbase can move freely to the filter, and then it can be collected from the pipe. It could also be applied for the base layer, which is called the base drain. Then the water collected from the base layer will move to the filtering on the side, and then collect in the pipe. So those are different type of designs depending on the inflows and also the properties, the permeabilities and the retention criteria of the base and subbase layers. And so those would be the design for the geotextiles. And for the pipes, the design is much simpler. First, for the pipes applied for the drainage system, usually they were made of the concrete, the clay, bituminized the fiber, the metal, the plastic with the smooth or corrugate surfaces and so on. So usually we will have the perforated, slotted, or the open joint for the under drain so that they can collect the water from the filtering layers. And so they will usually buried with the appropriate aggregates or the fabrics to filter the materials and or collect the water and also prevent the clogging. And for the outlet pipes, they will usually be placed in the trench and backfilled with the native soil. So those would be the it's quite similar to the sewer system. And for the filtering criterion, that will be very simple. For the slotted, for this slotted pipe, we want the effective size of the filter material divided by the slot width should be higher than 1.2. So that's for the filter for the slotted pipe. And for the for the pipe with the circular holes, then the D80 of D80 filter divided by the diameters of the hole should be higher than 1.0. If we are using the open joint pipes, then D80 filter, 85 filter divided by the maximum opening of the pipe should be larger than 2. And this will give you the, with that, you can select the appropriate pipes based on the filter material you applied in the pavement structure. So those would be the criteria for the drainage materials. With that, we finish all the introductions about the drainage materials, including the aggregates, the geotextiles, and also pipes. And the next thing I would like to include in this topic is the design of the procedures for us to conduct the design. And this one will mainly focus on the design of the slope about the pavement. If it's a super elevated pavement, then it will slope to one side. If it's in a crown structure, then it will have a slope to both sides. And for both structures, there would be some specific design about the filtering layers, and also they have different functions to calculate the flow, the inflow in the pavement structure, and how we can choose the pipes and also the filtering layers to remove those amount of the inflow. And I would like to save some time for the questions that we have for this class. And as next week is the reading week, you will probably can start to work on the lab report. And if you have already finished the soaked CPR test, you will have all the data for lab 1 and lab 2. Then you can work on both lab reports. So before we go to that part, do you have any questions about the drainage design so far, the materials of the drainage design, and also the procedures, not the procedures, the structures of the drainage system, and so on. If you have any questions, you can raise your hand, and or of course you can leave your message in the meeting chat. Also, if you don't have any questions, that's also fine. It's good. So for the lab report, as I say that there will be there's a sample about a very good report from the previous years. You can follow the sample to prepare your own report. We also have the lab report instructions to tell you what components you have to include in the lab report. And another thing which is very important in the report is like you have to do some discussions about your data, about the result you obtained from the analysis. There must exist some errors, some minor errors, or some instrument errors in the experiment, and you have to identify what's the potential errors in the report, and how you're gonna remove the errors in the future if you do the experiment again, and also what's the impact of the error to your result. Like if you have the CBR test and if you do not compact the sample very well, how it's going to affect the CBR, the California bearing ratio you calculated. Maybe you have a very loose sample at the very beginning, so that the penetration would be very high at the very beginning, does not follow the linear trend, and you need to do the correction. And if you are trying to do the correction, follow the instructions I showed in the class, and also try to explain the procedures you conducted during the experiment. With that, you will have well, for us, we will have a better understanding about your work during the experiment, and then it will be easier for us to judge the quality of your lab experiment and your lab report. Okay, do you have any questions so far? Okay, if no, then that will probably be all about the lecture today, and I will stop the presentation for now. And after the reading week, we will continue this lecture and try to finish all the details about the drainage design. And next week, we will also go, after the reading week, we will also learn something about the superplate and gyratory compaction test, which will be the demo that you can see in our lab. And of course, I will give you more details about how you're gonna access to the lab and what you need to prepare for the lab, for the third lab. You don't need to do it by yourself. It's just a demo. Okay. If there's no questions, I think that will be all today. And I thank you very much for your time. I really appreciate your attendance. And I hope you can enjoy your reading week. I know a lot of you will be very busy during the reading week for the other class. For our class, the midterm will be almost at the end of the October or early November. I've got the exact date. You can check the schedule. And I will give you some announcement about it in the on Emily to Learn. Okay, I think that's all today. Thank you very much, and I will see you in the other Monday.